Okay, let's expand upon what we were doing last section, 8.1, and let's do some more calculations, but this time we'll actually use a little more of the K expression that we've done in Unit 7. So, not really new, but we have K expressions, or we have K expressions for acids or bases. This is nothing different. It's just that it's showing the acid written like this. So if you would take some weak acid and put it into water, you would get hydronium and the conjugate base. So conjugate base and hydronium go up top. The weak acid goes on the bottom. Water doesn't belong because it doesn't have a concentration, and that equal a equilibrium constant, and we'll call it Ka. You could do the same thing with the base. They just use different letters and so forth. But that you can do IC tables, and we'll probably get away from writing the IC tables, but they're typically going to look like this. So we'll have x squared up top, and then whatever the concentration, maybe like 0.1 minus x will be typically 0.1. Remember, that's an approximation, so little squigglies there. But we'll figure out when we can make the approximations and when we can't. But typically we will be able to, because these Kas are often, not always, but they're often very small numbers. If you have strong acids, you don't bother with equilibrium because it's only single arrow. And there's some strong acids there. There's also some strong bases when we get to those. But we're going to be concentrating on these double arrows. And I wrote it last with the H2O attached, but the same thing. Here are our two products that are going to show up in the Ka expression, and here's our reactant that's going to show up in the Ka expression. We can also talk in terms of percent dissociation. That means how much, typically, how much, they're both the same coefficient, so it doesn't matter which one we use. Typically, people use the H positive because they might have a pH that they can get hydronium from. And so that would be our part hydronium divided by our total that we started with. So here's our strong bases, the same ideas that we had before. This is a good time to maybe mention this. If the acid's very weak, meaning that the left to right action is not very significant, the left to right action is much more significant, it does not dissociate, or very little does it dissociate. So we can talk in terms of this amount of dissociation with Ka values. Rank the acids from strongest to weakest. Well, I guess since this one says strong, HCl, you didn't have to know it was strong. We just had, you know what, let me not put the 1 there. We'll put it over here. Okay, so that is the strongest acid, meaning that this occurs. These two items do not have the ability to go backwards to make HCl. So that means that this Cl minus is the weakest of the bases. So if we were going to also attach some numbers to the conjugate bases, like which conjugate base is the strongest, well, if HCl is the strongest acid, Cl minus would have to do the weakest base. 1, 2, 3, 4, 5, 6. So that would rank 6. Basically, they're going to be opposites of each other. So now we look at the Ka value that is the largest. By the way, some textbooks might just call this large. I doubt that many textbooks are going to have a K value that's strong. And then lots of books won't even have a Ka value for HCl or any other strong acid. Our next strongest would be H3O positive, because that's our biggest Ka value next. Okay. And I guess we'll just go back, we'll just kind of walk backwards on these conjugate bases too. Next strongest is 10 to the negative fourth, not by much. 10 to the negative fifth. I'm not going to bother with the conjugate bases. They're just going to go in that opposite way to the acids. And then these are both, the next two are both 10 to the negative 10th, but 6.2 is just a little bit greater than 5.6. So ammonium is the weakest of these acids. So that would mean ammonia would be the strongest of the conjugate bases. Okay? So we're going to use that exact same idea to figure out, does this reaction go more left to right or more right to left? And whichever of these acids has a greater Ka value, that would be indicative of about which direction this goes more towards. So nitrous acid has a much bigger value than our other acid in question here. So this would be as if this is happening. So I think I've just kind of designated that it's going to go more left to right, and it's because of those Ka values not being the same. Which one's bigger is which direction it's going to move more towards. Do not use the quadratic. If you're going into the quadratic, something has gone wrong. Okay. Certainly, if you'd like to use the quadratic, feel free, but that's going to be probably a little more time-consuming than you need to be. I'll do one of these from start to finish here, but I would like for you guys to abandon this writing ICE tables down as quickly as possible, because they're going to be very similar. Okay, so that's going to be the setup. Ka value is given, 7.1 times 10 to the negative fourth equals x squared, because it's x times x on top, and then 0.5 on the bottom. Let's make that a better 0.5 there. And that's going to give you an x value. By the way, the x value could be A minus or H positive, but we'll love the H positive because that can be used to get pH. When we get an answer for X, that is 0.019 molar for H positive. So pH equals negative log of hydronium. So take the negative log of 0.019 and you get a pH of 1.72. Does that make sense? If I put some acid into water, I should get a pH below 7. Same item, different amounts this time. So same IC table, everything is the same. What the heck here? I don't know why I put 6.6 there. We were using in the last slide that as our Ka value. So let's keep using that as our Ka value. So Ka the only difference is that it's 0.05 at the bottom this time, and when we go and solve for X, it would give us 5.96 times 10 to the negative third. Now, let's go back to our, I'm just going to write a little bit of our IC table. and we had 0.05. If we would subtract x and think that's going to be 0.05, is that really the case? No, because this x value is going to have an effect on 0.05, and it has more than a, remember the rule of thumb for us is that does it affect it by more or less than 5%, and that number of change would have a pretty significant impact on 0.05 initial concentration of HF. So that means that if you wanted to actually solve this one, you got to use the quadratic formula. And we would not be using the quadratic formula on tests or on the AP test in May. You could get a question on homework with the quadratic, and you have the graphing calculator to be able to use to get your answer on that. So we didn't even get to the pH because we didn't like that answer for X. It's going to be in that ballpark of 5.96 times 10 to the third, but it will not be. So to save us some time, what I really wanted from this question is to show you that not all of these we'll be able to use the approximation for. Okay, so we have another acid. This time we have a pH. If you have a pH, you can turn it into a hydronium. And remember that the hydronium is going to be related to that X value. So it's going to be not only the X value for hydronium, it's going to be the X value for our conjugate base on the product side. So I'll show you this once, but I would like for you, again, for you guys to be able to get past doing that kind of idea. Okay, so 0 plus X is X, 0 plus X is X. So if we figure out what the hydronium is, we know both of those X values. So pH is 2.39, take the negative anti-log, and the hydronium is 4.07 times 10 to the negative third molar. So if we wanted to get the Ka value, Ka is going to be 4.07 times 10 to the negative third squared, because we have X times X. And then on the bottom, we were told we had a 0.1 molar solution. There we go. Weak bases. You got some choices. Your textbook uses that choice to write the base reaction. I prefer this method. It's up to you. I could, if you don't want to use any A's or B's, you want to use your own letters, that's fine with me too. But let's look at the one I circled here. So the KB would be HA concentration, hydroxide concentration, and then the base concentration on the bottom, just like I showed there. Okay. If you wanted, by the way, to go between Ka and Kb, why would you need to do that? Because sometimes maybe you can find ammonia in the back of the book for Kb value, but maybe you can't find ammonium. So if you wanted to go from the Kb to the Ka, there is a method for you to do that. What's the pH of 0.4 molar ammonium solution? And we have a Ka given. So Ka is going to equal X squared up top and 0.4 on the bottom. Wait a minute. Wait a minute. Ammonia, ammonium. So ammonia is NH3. Here's our water. It's going to make ammonium and hydroxide. ICE, we need, this is a base reaction. There's a couple ways you can know it's a base reaction. It makes hydroxide, which is a conjugate base. But you need a Kb expression. We don't have a Kb, we have a Ka. So 1 times 10 to the negative 14 divided by 5.6 times 10 to the negative 10th equals the Ka. And I think that's going to be 1.8 times 10 to the negative 5th if you do that on your calculator. So we'll see what we get with that. 1.8 times 10 to the negative 5th times 0.4. Take the square root. And that x value is either of those two, but I don't really care about the ammonium if I'm trying to get a pH. So that is the, we'll put it down here as the hydroxide. If you want to go POH, you can do that. Just hit the negative log. And then pH would be 14 minus that. So what's the trick on this one? You have to remember to turn a Ka into a Kb because it's a basic reaction, not an acidic reaction. Okay, what do we got here? We have a Kb this time. Okay. And we have a base. So if we have a pH, we could turn that into hydronium, or we could turn that into POH. So 14 minus 9.5 would give you 4.5 for the POH. And then take the negative anti-log to get to hydroxide concentration. That says 5 there. And why is that important? Because we have our base plus water. You could write it whatever way you want it here. You could write the C5H5N. You could write it in your head if you wanted. But ultimately, that's going to make, I guess we have to call it that and that if we want to make these look the same. But anyhow, 0 plus x is x. 0 plus x is x. So that value that we just calculated is for either of those two x's. So this time Kb is given 1.7 times 10 to the negative 9th. We have our 3.16 times 10 to the negative 5th. Really it's squared because it's x times x. And then we don't know that on the bottom. There's our answer. So that's the initial concentration of that base. And we have one more. I think we have a couple more questions. pH. Same exact kind of setup this time, except now we're solving for the KB. So we have a pH. Can we go to pOH first? pH minus, 14 minus pH will give you pOH. And if we have a pOH, we can get to a hydroxide concentration by taking the negative antilog. And again, our setup was the same as the previous question, just the previous question we solved for KB. No, we solved for initial concentration. This time we're solving for KB. 3.31 times 10 to the negative third times 3.31 times 10 to the negative third. I'll just put squared there. And then at the bottom, the initial is 0.1. So when we solve for KB, (1.1 times 10 to the negative sixth). Okay, percent ionization. All these percents are the same. It's the part that we're interested in divided by the total. This means initial concentration of the weak acid, and this would be the H positive that we could have determined using a IC table or pH. We're going to prove this, but you could memorize it too if you wanted to. But the more dilute the weak acid, the more it will break up into its ions. So we have acetic acid, 0.5 molar, Ka equals x squared up top and the 0.5 on the bottom. Solve for x. And that equals the hydronium. It also would equal the acetate. Those are the two products in the ionization setup there for the weak acid. Let's go down here at the bottom for the 0.05. Let's do the same exact setup. 1.8 times 10 to the negative fifth equals x squared again, but this time it's 0.05. Okay, so neither of these two questions had we actually answered the question yet. It says, what's the percentization? So that is our part divided by our total times 100. And then down here, 9.5 times 10 to the negative fourth divided by 0.05 times 100. So we started off with a smaller concentration of weak acid, and we ended with a greater percent ionization. Couple multiple choice questions. Like always, we got these answers C and D, but let's figure out why. So we have a acid. Monoprotic means it has one H positive, has a pH. What's the Ka? So Ka equals, if you take this pH and turn it into a hydronium, that would go on the top of the fraction. And since it gave us a number that is a whole number, it makes it very easy on us. So it's 1 times 10 to the negative fourth times 1 times 10 to the negative fourth, and then the bottom 0.1. And you know what? Let's actually change that. Let's make that 1 times 10 to the negative 1. So 1 times 10 to the negative 4th squared is 1 times 10 to the negative 8th, and then 1 times 10 to the negative 1, and that means that equals that. That's all without a calculator. We have caffeine here. Caffeine has a KB value, and a pH is given. So KB, 4 times 10 to the negative, let's kind of divide these two here. Questions. pH doesn't do you any good if you have a KB value, but a pOH does you lots of good. Oh, I was thinking the question was going in a different direction. It's asking which of these answers has a whatever pH. So KB equals x squared up top, and 0.01 was our initial molarity on the bottom. And let's not use that 0.01. Let's use 1 times 10 to the negative 2. So if you isolate x squared, that would be, I think you can do this in your head here. It would be x squared equals 4 times 10 to the negative 6th. And then x would be 2 times 10 to the negative 3rd. That's going to be difficult to do in your head, but 1 times 10 to the negative 3rd is going to be in the ballpark, because all we need is a ballpark. And that would give you a pOH of 3 and then a pH of 11. Bingo. So yes, you're going to have to make some approximations with some of these multiple choice questions. And I think we have one more of these here. Yeah. And answer is already given to us as B. K greater than 1. What does that mean? More of this, less of that. So this and this and this are stronger than the components on the right side. So it asks us which is the strongest base. Well, HX can't be a base. That's an acid. Anything with the H's in front cannot be. So the only bases are those. So since it moves more left to right, whatever stuff is on that left side is stronger. So that's how we got an answer at B. And that concludes this section.